This short video will demonstrate proportional control on the SCUTTLE robot. So first of all, we're running a program called L3 PID Lab, and we're calling a loop that is asking to drive in the closed loop feedback control method to reach a certain phi dot targets for left and right wheel speeds, and it feeds in the current phi dots that are being measured in real time, and it feeds in the delta in time from the previous sample to the current sample so that derivative control can be implemented if necessary. But right now we're just dealing with proportional. So what else I have implemented is that we're pulling the KP value, which is going to be the proportional control constant. We're pulling that from a file that we're setting in real time, where 0.04 is our nominal. It's kind of our starting point, but after we get sampling, we're going to pull the value from kp.txt, and that is over here. And I won't open it up so I don't break anything, but it's basically going to come from the Node-RED dashboard. I have three tabs. The kinematics tab right now is measuring the phi dot left and phi dot right wheel speeds in radians per second. And right now they're going almost as slow as they can go before they stop, about 1.5 radians per second. And obviously they're oscillating. This is not the phi dots, this is the actual encoder readings. So disregard the encoder readings for right now. So let's go to our code. In here, we've set our phi dot targets to be, we're feeding the phi dot targets left and right. That's in the speed control, and in our level 3 function, or level 3 program, we are choosing our targets. So right now it's 9.7 radians per second for both left and right wheels. And clearly, based on our dashboard, we're not getting 9.7 radians per second. So let's show how this is being implemented. First of all, the control is just driving the KP value. Right now it's set to 0.04. We can increase it to 0.05. And you will observe a small increase in these wheel speeds, even though we didn't change the targets. And here's how that's calculated. This is just using an example of wheel speeds that have been logged to a log file. These are sample numbers that are separated by, I think, less than 1/10 of a second. The speed that we were achieving, understand that the speed also has its own error based on the encoder rollover and the encoder sampling rate and the encoder resolution. And then we have our target. So for any control system, your error will be defined as the difference between the target value and the current value. So in our case, this error is calculated by 9.7 minus 1.36. So in a previous iteration, where our target was constant and our speed was far lower than 9.7, that gives us an error of 8.3. So how does the KP value get implemented? Well, what the KP value does is it says we're going to proportionally control our driver or our actuator. In this case, it's a PWM output on our motor drivers. We're going to proportionally control that by 0.04 times whatever error we've discovered. So in this case, if our KP is 0.04 and our error is 8.3, understand that in the very first sample our error is going to be the entire target because the speed is 0. But if we have some nominal error around 7 or 8, we're going to multiply that by our KP, and then we're going to feed that value to the motor driver. So 0.33 is going to be the full control effort. In this case, we call that UP, or U sub P. And U sub P is going to be 0.33, and that will also equal U total, since we're not using integral or derivative control. Then this 0.33 will mean that 33 out of 100, basically 33% of the time, our signal to the motor driver will be high, and the remainder of the time the signal will be low. So when we have 12 volts coming into our motor driver, and only 0.33 out of 1 times that 12 volts is going to be passed to the motors. In the result, we have a speed that's far less than the maximum speed. Just so that you know, our typical maximum speed when the vehicle's on the ground and unloaded, the maximum speed typically is 9.7. So if you gave a duty cycle of 100% to the motors with 12 volts on the ground, you would achieve somewhere around 9.7 radians per second on left and right wheels. In this case, we're only giving about a third of the voltage, and it's just barely enough to actually drive those wheels from a standstill. Since the motor's spec'd at 12 volts, it's not very typical to ask that motor to even move at all under load when you're only giving it less than half of the voltage. So we come over here and we can increase our KP. Right now it's 0.05. We can increase that to, let's say, 0.07. And audibly, you can't hear on the microphone, but I can hear my wheels have increased in their speed. And right now we're achieving about 3.5 to 4 radians per second. So that means when the new value is calculated for the control signal, it's actually not going to give you 0.04, or it's not going to give you 0.07 times the original error. It's going to give you 0.07. This is what you'd get instantaneously. You'd get 58% duty cycle. But since our new speed is actually somewhere around 4.5 radians per second, we're still back down to a little bit lower KP. And then we're going to have these oscillations where the motors swing up and down, and the further once the control signal increases, then they're closer to the target. The following sample will decrease the control signal. And when the control signal is decreased, then the wheel speed is going to fall down again, and we're going to give a higher one. And that's how you end up with the oscillations when you're just dealing with KP. So hopefully this gives you a starting point to understand KP in your control system.